Okay. Okay. Oh, that was loud. Sounds different, right? Well, I'll be less loud than normal. We've discussed in the previous lecture. Let me ask them to reduce that. Okay, so we covered how to develop solutions for springs, trusses, and in the last lecture we actually covered various partial differential equations as applied to various problems, such as 1D solids, elastic bar, ordered Bernoulli beam theory. We covered plane stress, plane strain, 3D bodies. We then covered heat transfer problems in 3D and 2D. Then I covered partial differential equations as they apply to 1D problems in general. Okay? And so what we're doing here, I'm setting the problem up for you so that we can now talk about how to approximate solutions to partial differential equations. Can somebody remind the remaining of the group here, what is finite elements about? What are we trying to do with finite elements? Somebody please, you've had a couple of weeks now to think about how to say that in class, so I request that you help me out. Please.
You just discretize the geometry into simple elements and then reconstruct them and then solve it as a whole.
So the answer you're giving is that you'll discretize the domain into smaller subdomains, and then you'll then assemble the behavior of the structure together and solve the equations, right? But we want to say a little bit more. So we want to say that what we're trying to do is to solve a partial differential equation that could be related to a physics problem, all right? And what you're trying to do is solve the partial differential equation for a domain that may not be of simple geometry. And for that reason, what we're trying to do is break up the domain into smaller subdomains that we can now more easily solve these partial differential equations in those subdomains, and hopefully we can then assemble the systems of equations that we can reconstruct. I like the words you use, the behavior of the structure, and then we can solve now a partial differential equation using a system of algebraic equations, which could be linear or nonlinear. Is that clear? Are we memorizing what finite elements is? Like, why are you here? You're here to basically use finite elements in real life. You may go to industry or you may do research, but at the end of the day, you're really trying to solve a complex problem broken down in a little bit simpler way. And if you go to industry, then the goal for you then is to understand what the code is doing behind the scenes. So you're not using the code blindly, right? And if your goal is to pursue a PhD, then your goal should be, I want to learn how these elements are being formulated so I can then maybe formulate my own elements. Or if I need to couple piezoelectric with solids, I can do that. Whatever you're trying to do, I'm trying to give you the tools necessary to accomplish that. Okay? Everybody's clear on what we're trying to accomplish in this course? So today we'll be, for the first time, talking about how to approximate the solution to a partial differential equation. And you'll be, I think, impressed how this methodology was developed and how well it works. The first method that we'll discuss in how to approximate the solution of partial differential equations is called the strong form Galerkin. That's the first method we'll be discussing today. And this is one of the first three methods we'll be discussing. And just to summarize, the basis of finite elements is really to approximate the solution of partial differential equations. And we've described the steps. And I described the steps in previous lectures, but I want to repeat it. So the first step is to derive the PDE equation, the partial differential equation, for the problem of interest. And that's what we did in the previous lecture. Then what we want to do is formulate the solution of this partial differential equation over an element which is of simple geometry. Okay? And then after that, I'll go ahead and discretize the domain into smaller subdomains, which have this simple geometry that we talked about. And then we'll assemble the system together and then solve a system of linear or nonlinear equations. And so in all of this, we haven't really yet talked about how to solve the partial differential equation into in a simple geometry yet. But we're going to start making movements towards that. We're going to make stepping stones towards that. And so in today's discussions, we're simply talking about how to approximate a solution to partial differential equations. And I'll be discussing that in few problems coming up. Okay? There's three methods that we'll be discussing in this course. Today we'll discuss strong form Galerkin. On Tuesday, next week, we'll be discussing weak form Galerkin. And then after that, we'll be discussing a method called Riley-Ritz. And so today I will start the discussion with strong form Galerkin. So I think one of the best ways to sometimes teach a concept is to start with showing you a partial differential equation, or differential equation in this case. What is this differential equation for? The first one here, as an example. That's for a 1D bar, elastic bar. And the one here is for a beam in bending, right? So is everybody like keeping up with me right now? So you've seen these two partial differential equations in this case. And what we see here is actually what we call the strong form of the problem. So these two right here, these differential equations, as you see them, they're called the strong form of the partial differential equation. Because that partial differential equation is mathematically valid at every point inside the domain and at the boundaries. So it's a true statement at every point in that domain. That's what makes it the strong form. Is everybody clear on that concept? Very simple concept, but we'll be making these concepts a little bit more complex as we go forward. You have a question?
What's the distinguishing factor then of a weak form?
I'll be discussing that. So the question in the audience is, what distinguishes strong form with weak form? And I'll be covering that moving forward. Do not worry. I'll get you there. But if I explain it now, I think you guys will be confused. So give me a little bit of a chance and we'll get there. Okay? Moving forward here, I'm going to form something called a residual function. Okay? All I did here is I took this Q and put it on the other side of the equation. Okay? And I'm going to call that R. And we'll call that the residual function. And so this residual function, including the boundary conditions, comprise a residual. Okay? And this residual function, everybody agrees that if I change the value of W, R changes? Can you see that happening? Okay. What is the primary variable of interest here? What are we trying to solve for? W. The displacement W is what we're trying to solve for. And so if I change the value of W, the residual function is going to change in value. If W happens to be a solution to the partial or differential equation in this case, what happens to R? R, the residual function, will become 0. I'll get the original partial differential equation. So if W is a solution, then R is 0. That's clear to you, it appears. And not only that, if W is not a solution to this differential equation, then I think you will see very clearly that R is not 0. Can you see that happening? So if W is not a solution to this problem, then R is not 0. Now, these are obvious things, but I think it's important to discuss them because these forms the fundamentals of finite elements. We're moving forward in that direction. Okay, and so when I now look at the strong form, now I say let me do something. Let me formulate something called a weighted residual. And so what I've done here is I've multiplied the residual function that we discussed earlier, and I've multiplied that by something called a weight function. And I multiplied these two things and integrated this from 0 to L. Okay, I'm formulating that, and for now, you may ask me why I'm doing this. And I think the reasons will become apparent. But you know, the underlying reason is when the residual function is non-zero, my goal is really to try to find a way of minimizing that residual to 0 so I can find a real solution to the problem. Okay? If, I want you to notice this, if W is the solution to the problem, can everybody see here that this residual function here equals 0? Yeah? And it turns out that if W is a solution to this boundary value problem, and R, this residual function, is 0, there's a very important lemma, and it comes from calculus of variations, which you'll learn a little bit, not in a very deep way, but you're going to learn it a little bit. It turns out that this fundamental lemma of calculus of variations states the following. If this function, which is a residual function, is 0, then the integral of this residual function, which is actually equal to 0, multiplied by arbitrary admissible functions, weight functions, that this integral is going to be equal to 0. That's what the fundamental lemma says. And if you're interested in the proof to that lemma, I can point you to some books that will help you see that. But the bottom line is, what we're saying here is that the multiplication of a residual function and W being the solution to the problem, that multiplied by V, which is a weight function, that multiplication gives you 0 over the integration, integrating that multiplication over the domain of the problem. Okay. And so it turns out that the opposite is also true. And the opposite is the following. If the integral from 0 to L of this residual function times this weight function, which is arbitrarily chosen, times dx, if that is equal to 0, the fundamental lemma of calculus of variations also implies that for any arbitrary functions here, Vx, that R is equal to 0. So it also implies the other way around as well. And so it turns out that if the displacement field, Wx, satisfies equilibrium, in this case the equilibrium of the beam structure, subject to transverse loads, that you'll have a vanishing residual integral, meaning that this integral will go to 0 for any weight functions Vx. Okay? And one of the important things in this theory that we're discussing is that this this function W here must satisfy all the boundary conditions of the problem, essential and natural boundary conditions. Because as we discussed before, we're talking about the strong form of the problem. Okay? And for the strong form of the problem to be really a strong form of the problem, the partial differential equation has to be true at every point in the domain, including the boundaries of the problem. Is everybody very clear in what I'm discussing? These are very fundamental concepts that may appear simple at the surface, but they're actually quite complex going deeply. So I want to make sure everybody here understands what I'm talking about here. Okay? And mathematically, this is equivalent to a strong form, what I just wrote here. But quantitatively, in reality, we're basically saying that equilibrium of this body, on average, is equal to 0. Okay, so I've achieved equilibrium on average because I'm integrating over the domain. But mathematically, this is a true statement, and it's an exact statement. Okay, so let's look at now at how to approximate the solution to this strong form. I'm sorry, to the strong form. And the strong form, when I say strong form, that's a partial differential equation or the differential equation we discussed. To approximate the solution of the problem, I'm going to go and set out and say, you know what, I don't know the solution to the problem, but I'm going to assume an approximation function. And in this case, I'm going to assume an approximation function that has a function here, okay, which I'll discuss later what this is, plus a summation of unknown constants, I don't know these constants, times some functions. And these functions are known. We know the shape of these functions. We know the shape of these functions. So we know what these functions are. Okay. The only thing unknown here is CI. Okay, so bear with me and you will get it with different examples. And I'm going to use a lot of matrix notation because as we move forward in finite elements, we're going to use a lot of matrix notation. And the reason that's important that we're doing it with matrix notation is because, again, just to emphasize, finite elements provides a systematic approach to solving partial differential equations. So if I can set everything up in matrix format, then now I can assemble the systems, the different elements together, and I can code up in Fortran or C++ a much easier way of assembling everything together and solving the algebraic equations. And so what I'm going to do, by convention, I'm going to put this vector phi, which is going to contain all these functions here. It's going to contain the functions that are known. We have selected them in a very careful manner, and I'll explain them how we select them later. So can you see here that W, the approximation function, the only thing that's unknown here, will you agree is CIs, if I know the phis, the function's phis? Okay? As an example, a function phi could be, phi1 could be x, phi2 could be x squared, phi3 could be x cubed. In a particular problem, that could be the case. So the only unknown really is Ci. And so typically when you write a vector typically is n by 1. So it's going to have a column, and it's going to have n rows times 1 column. Okay? And so when you take the dot product, you'll get Ci phi. But by convention, we're going to define phi so that phi is 1 row times n columns. Okay? So then I can really perform this multiplication correctly. So this multiplication times C, and C actually is a column of unknown, C1, C2, C3, C4, C5. You can quickly see that the dot product of this times C1, C2, C3, C4, C5, Cn, that multiplication gives you that. Everybody can see that? That gives you that? Yes? Okay. So the only unknown is really C. Okay. And the idea is to take this approximation function and minimize that weighted residual function that we created earlier. And so to do that, and please don't read ahead, just follow with me so you don't get confused. What we do is we take the approximation to the solution and we plug it in here. So this is my residual function, and I'll plug in the approximation for W in here directly. Okay. And I will make this residual, which now we agree that this residual here probably has an error now, because I didn't put the exact solution in for W. I put an approximation in. So would you agree that R is not necessarily equal to 0? And that R is 0 if the approximation function is selected the perfect one. Okay. So what I will do, I'll make this residual function, and I'll make it orthogonal I'll make it orthogonal to the space of what we call basis functions or weight functions. Because if you make the error orthogonal to the shape or to the basis functions, what you're really doing is you're minimizing the error. And so what I'm going to do to do this, I'll take the residual function, which has approximation embedded in here, and I'll make this R, and I'll make it multiplied by VIX, which are the weight functions. And I'm going to make the weight functions go from 1 through n. So if we think about this, and let's say that V is known. We know V for a second. And I'll explain how you will select V in a second. How many equations do you see here? How many equations we see here? I have n equations because I'll make I equals 1 for the first equation, I equals 2 for the second equation, I equals 3 for the third equation, and so on. And W tilde, I basically know it except for the unknown coefficients. How many unknown coefficients we have? N unknown coefficients. How many equations I have here? N. So I can solve for the unknown coefficients. And trust me, it's beautiful. It works. Ask my students from 261A. It does work. And I'll show you that in 5 examples. We'll go through 5 examples. And it's kind of eye-opening that it works, actually. So we will look at how to do this now. And, you know, there's a lot of math. But if you follow the steps, you will not be confused. You just need to follow the steps and trust the math background that you've gathered before this course. Everybody here, what I want you to understand is that these functions V, which are the weight functions, in strong form Galerkin are chosen on purpose to be the same as the set of basis functions. So earlier I called this the basis functions. Okay, these functions will be the ones selected for these V's, for these weight functions. And it turns out if I make the error, the error, residual function error, and I make this orthogonal to each of these basis functions, and I make that equal to 0 for n, j equals 1 through n. So the first equation is making j equals 1. Okay, then I make the same equation, j equals 2, and so forth. And all I did is insert here the approximation for w. So I inserted that there. That I have n unknowns, and I have n equations. Okay, and it turns out this will actually give you the solution to these unknown coefficients. So in matrix notation, which I think is very important for us to get a good grasp of, because so the previous notation is great, and I recommend it very strongly that when you do the problems, do it 2 ways. Do it with the long way, write it, enter everything in here by hand, and it's kind of painful, and then solve these equations maybe using Mathematica or MATLAB. But I do want to encourage you to also use matrix notation because that's the direction that we're moving in this course. We're trying to get to a point where we can just work with matrices. And so will you agree that W is this? So I have a phi sub 0 plus, what are the unknown coefficients here? Remind me? C. These are the unknown coefficients. Phi is the basis function, contains the vector of basis function, so that's phi. And what I'm going to do, I want to see what I did there. I'm going to take this phi jx, and I'm going to make it phi transpose. So what you see here in the next slide, I made a phi transpose here. And if that makes sense, let me explain to you why that makes sense. So in the previous slide, can you see here that phi 1, phi 2, phi 3, phi 4, up to phi n? Basically what you have is a column of phis. You see that? So if you were to write this in matrix notation, this phis now became the phi transpose. If you remember earlier, phi was defined so that it went like this, right? Left to right. So that's 1 by n columns. And so phi transpose basically took that and made it n rows by 1 column. So that makes sense because if you look here, that's really what I have. I have the first equation as this times phi 1, The next equation will have this times phi 2. And you can see it's basically a column of phis. So I'm going to make that phi in matrix notation. All you have to do is make a phi transpose and put that at the beginning. Okay, at the beginning. Now, to keep track of what we're doing, because I think it's very important to understand what we're doing here, I want you to notice that phi transpose is how many rows times columns? N rows times 1 column. That's what I have there. So keep that in your head, okay? And then phi here is what? 1 row times n columns. So in reality, this phi transpose times phi should give me a matrix n by n. Can you see that? Can you follow me? So if this is n rows times 1 column, so n rows times 1 column, multiplied by 1 row times n columns. That should give me n by n, a matrix that is n by n. Okay? And so now, you can see also here that I can expand all this. And here I made these derivatives to be primes, because it's a little bit easier to write. And I can expand it out. So I can make this multiply that times that. So that's what I did there. That multiplied times that. So everything is expanded out. Now you can see very quickly that C here is the unknown, and it does not depend on dx. Can you see that? C does not depend on dx. So what I will do, I'm going to bring C, and C is only multiplying this. So the C can come out of the dx, and then I'll have this C, and then this term is that one, and then this term has no C, but the phis are known, you know? You agree the phis are known? So I'll bring this to the other side of the equation, and I'll bring this to the other side of the equation. So what I end up getting is phi transpose times that minus phi transpose times q. Okay? And I think I see a small error, so there's a transpose missing here and a transpose missing there. So can you take a note so I can correct that? I don't have the slide number here, I'm sorry. But we need to correct that. So now, I want you to see if you agree with me, but are all these things something that you can actually calculate? Yeah? I can calculate all these numbers. The phis are known. The integral of that should be fairly easy to calculate. And then all these matrix or this integral can be calculated as well. And so all I have to do is invert and get C, the unknown coefficients. So let's expand that out so you can see how that works. So phi transpose is the first column here, phi 1 up to phi n. Then expand EI phi double prime, and that's this. Okay, and the C's are written here, and then I have the phis there, and I have expanded everything out so you can quickly see that it works out. Okay, can you see that it works out? It's going to multiply very nicely. And then in the next slide, I show you the multiplication, how everything looks in multiplicative form. And so all these can be integrated 0 to L. Okay, another error, it should be 0 to L. Each of these should be 0 to L, so I'm missing a 0 to L. I think something's getting cut off there. Okay? And so now all I have to do is invert the stiffness matrix and calculate the C's. Okay? All right. So I see a lot of you don't know if you follow it 100%. So are you following me, or is it too abstract? So let me summarize it for you, and then let the math follow up with you. Okay? So what we did, we came up with an approximation function. I don't know the exact solution, say, to the partial differential equation. So I'm going to assume an approximation to that partial differential equation or differential equation, and I'll plug in that approximate solution into the differential equation. That's all I did. So what did that cost me to have? By putting an approximate solution into my differential equation. An error. That caused an error because it's not the exact solution. So I took the error and I made it orthogonal to the set of basis functions, the set of functions that made up my approximation function. And I integrated that over the domain, 0 to L. And because I took my residual function, error function, and I made it orthogonal to each of the functions that made up my approximation functions, and there are n of them, then have n equations and n unknowns. And so I can solve for my coefficients, unknown coefficients. Okay? And I think this is better illustrated with numerical examples, but I think it's important for us to at least initially understand the theoretical concepts. And so, how we select these basis functions? How do I select these fees? How do I select these fees? Okay, there's a set of rules we need to follow. You cannot just select any fees. Okay, one of them that I think is very easy to point out. Okay, let's say phi is a cubic function for a second. Say the phi started at x squared x cubed, okay, a polynomial up to x cubed. Can somebody tell me what happens to this differentiation if the approximation went only up to cube term, x to the cube? How many of you say 0? Use your intelligence to answer. So if I have terms that go up to cubic, x cubed, what is that fourth order differentiation on that cubic term? The first derivative makes it quadratic, right? The second derivative makes it linear. The third derivative makes it constant. The fourth derivative, 0. I have a problem. Then I will get 0 minus q, and that will never be equal to 0. So one of the rules is to make sure that the approximation function you select here can be sufficiently differentiable, and in this case, differentiable up to the order of the differential equation. In this case, it's fourth order, so a cubic term will not work because it will give me 0. So it needs to be sufficiently differentiable. Another rule that should be followed, that has to be followed, is that the functions that you select for the fees should be continuous. They cannot be discontinuous functions because we need to take derivatives of these functions. We also want to have functions that are complete set, okay? And that will be covered in the next one. So here you can see, here phi 1 is x, phi 2 is x squared, but then I skipped x to the 3. That's not good. I need to have a complete set of functions when I use this method. One of the reasons says that the behavior of these differential equations such that is made up by summation of linear behavior plus constant plus quadratic. Well, by me skipping those terms, it doesn't matter. Say the solution is constant. That the differential equation, the solution to that differential equation is that the value is constant over the domain. Okay. If I skip all these terms and I just select phi 3 equals x to the 4th, will I ever get the exact something that's approximate the solution? No, because x to the 4th is a polynomial. It's not constant. So I need to be able to represent the behavior of every constant, linear, quadratic, and so forth. Okay. Is everybody clear? Any questions so far? Any questions so far?
Could you go over again what you said like 2 minutes ago? That when you have wave function is cubic, and then
You want me to discuss again why when I go up to cubic alone, that's not good enough? Yeah, so let's do that. So if I enter this cubic term, this cubic approximation in here, if I differentiate once, what do I get? Quadratic.
yeah.
But I have to differentiate this 4 times.
Right.
So this is going to go to 0. This differentiation is going to go to 0.
Yeah.
So then I get 0 minus q. Q times phi. Now I have no unknown coefficients to solve for. And only that, this will never be equal to 0 because now I have this 0 minus q, q times phi. That's not going to work. Okay? Okay, so I think this makes sense to everybody. Each of the set of basis functions we select have to be linearly independent. So if I choose phi 1 equals 1, phi 2 equals x, and so forth, each of these is linearly independent. And there are linearly independent. They don't depend on each other, right? This one also is linearly independent. You know, each of these, like this one does not depend on that. This one does not depend on that. In example 3, however, you can show actually that this is a linearly dependent set because these functions can be written in terms of the other ones. So if I write phi3, I can actually write it in terms of phi2 and phi1. So that's not linearly independent. Okay. So the set of functions you select for phi, they have to be independent from each other. Okay. Otherwise, you will have a singularity. Things will not work out. Another condition that's extremely important for everybody here to follow is that with strong form Galerkin, that each of the basis function, each of these basis functions has to satisfy the homogeneous form of the boundary conditions of the problem, essential and natural boundary conditions. Okay? So they have to satisfy all the boundary conditions of the problem in its homogeneous form. And when I say homogeneous, is the boundary conditions are specified as being equal to 0. Finally, we have this phi sub 0, which I haven't discussed yet. This phi sub 0 is not really a basis function. The only purpose of this phi sub 0 is there to satisfy boundary conditions for which they're non-zero. So if, say, I apply a displacement of 1 at the end of the bar, the purpose of this particular function here is to ensure that you satisfy that boundary condition. Because remember, these ones here, the purpose of these ones will not satisfy that boundary condition. That one is going to satisfy the homogeneous form of that boundary condition. And I'll give some examples to illustrate this so it becomes more apparent. Okay? I think you have a lot of questions in your mind, but we'll try to walk them through one by one. Okay? So let's take the first example. I think the first, an example, we'll do 5 examples. 5 examples, and hopefully through 5 examples you will get it at the end of the day, okay? I'm hoping, okay? And if not, again, I'm here after class as much as you want, and then we have office hours and a discussion class tomorrow as well. And so we'll take this example. Here's a 4th order differential equation. It's subject to a distributed load. And I think everybody knows here that in a beam, if I have a pin-pin condition, that W, the transverse deflection is 0. The transverse deflection is 0 here as well. Okay. What is the primary field of interest here? Displacement. And I'm specifying a boundary condition on that displacement. What kind of boundary condition is that? Natural or essential? Essential, because I'm specifying values on the primary variable of interest. In this case, is W. I'm specifying there's 0 here and it's 0 here. So that's an essential boundary condition. That's an essential boundary condition. And then now I also know for a fact that here there's no load applied at this end. Do you agree? There's no load applied there, and there's no load applied here. Okay. So in that case, the moment. Do you agree? There's no moment applied, and there's no moment applied here. So then we know then that W double prime is 0 and W double prime L is 0. Okay, because if you recall, moment equals, if you recall from the previous lecture, moment equals EI W double prime. So if moment is 0 because I'm not applying it, then W double prime is 0. What kind of boundary conditions are this? Natural or essential? Natural. Because they are not the primary field of interest. They're not the primary field, they're secondary fields that depend on the primary fields. Okay? And so now my goal is to find the solution to this differential equation. That's what I want to do. Okay? And you guys know the exact solution. The exact solution, you go and integrate this 4 times. You have 4 constants of integration. You apply these boundary conditions, and then you get the constants, right? But let's presume for a second, just pretend with me for a second that I don't know how to solve this, right? So let's pretend that. And so what I'll do, I'm going to select a function that looks like this. W tilde x equals C1 sine pi xl plus C2 sine 2 pi xl. Now, let's check this out. does this look like is complete? So it looks complete because I didn't skip any terms. I went from pi xl to pi xl. I didn't speak, I didn't go to 5 pi xl. I went straight to 2 pi xl. So that looks complete, number one. Number two, is it sufficiently differentiable? Can I take 4 derivatives of this? Yeah, I can. Good. I passed that test at least. I need to also make sure that the boundary conditions, this basis function satisfy the essential and natural homogeneous form of the boundary condition, meaning that each of these has to be equal to 0, okay, essential and natural boundary conditions. So what we can do is just check that my approximate solution actually works out. So W is 0, do I get 0? That's the question. So if I plug in 0 here, yeah, I get 0. You agree? If I plug in L in here, L and L cancels out. Sine of pi is 0. Okay, so that's 0. And then this one is 0. So it's working out so far. Let's check double prime 0. So double prime 0, if you take 2 derivatives of this, you'll get sine again. Sine, cosine, and then sine. So you're back to sine. And so in essence, I think it's kind of obvious. If I put 0 here, the signs will go away. And then for L, I'll get basically the same thing I got here, repetitive. So this is a great approximation function, other than it's painful to integrate and do all kinds of stuff. But the important thing I'm trying to illustrate for you that this is a good approximation function. And then this, actually, if you were to solve it and you got the numbers out, it's going to match. It's going to match. It's going to get really close to the exact solution, actually. Okay. So let's see what we do now. This is clearly not. I mean, the exact solution to that differential equation I showed you is really a polynomial. Everybody agrees? I mean, it's a polynomial. But I chose a trigonometric function, which would have been my last choice. But that trigonometric function, by me choosing that, what does that do when I substitute that into my differential equation? It introduces an error. Very good. He's on top of it. He's the only one answering today. So let's take a couple of minutes break. Okay. Wash your for you. Okay, with that said, I'll continue the lecture. Now that I think you're a little bit awake, if I were to substitute the approximate solution in this differential equation, what will I get? An error. Thank you so much. Finally, we're getting participation. And so if I substitute this approximate solution, now I will have an error, and what I'll do, I'll take a residual function, which is this one, and I'll make it orthogonal to the weight function here, Vx, which I'm going to select as phi1, and I'll select it as phi2, okay, in this example. And so what I've done here, I've inserted here the approximate solution for W, and I've taken that differential equation and made it orthogonal to phi1. Phi1 is sine pi xl, okay? And then for the second equation, I've done the same thing, but then I've switched phi2 to sine 2 pi xl. Okay, so how many equations do you see here? 2. How many unknowns do you see here? 2, C1 and C2. You agree that these are, we can probably integrate this using maybe Mathematica and so forth, and you should get a 2 by 2 matrix, which is a linear system of equations, which I can solve for C1 and C2. Okay, that's the first example. Okay, and so for 10 points extra credit due next Tuesday, if you go and actually do it at home, and you compare the solution to the approximate solution, sorry, to the exact solution, you compare them maybe using Excel or Mathematica, and you can show that this actually works out, you know, that's a good opportunity for you to pursue. Okay. From my own experiences, the more you practice this stuff, the easier it becomes to follow. Okay, because this looks messy, right? But I want to show you that when you actually do it at home with calm, that things do work out very nicely. Let's look at the next example, example 2. I'll do 5 examples. We covered example 2 now, example 1 now, 4 more to go. Example 2, I have this elastic bar, and this elastic bar is fixed here and then fixed here. Okay, so with that said, what are the boundary conditions of this problem? Are they essential or natural? Essential. Why they're essential? Thank you for participation. That's what I'm looking for. So you've said it's essential. Why you think it's essential?
It's related to the displacement, the derivative of the
Very well. He said it very well. So because I'm applying values, I'm prescribing a value of 0 on the displacement, which is the primary field of interest in this differential equation. And later on Tuesday, I'll show you a more clear way and a more mathematically correct way of saying which is essential, which is natural. I'll discuss that on Tuesday. But for now, we're using the primary field of interest as a good guide on what is essential and what is natural. And so, and this one is under distributed load P. And so for this example, I made EA to be constant, so I can just write a simple differential equation here. And this one actually is very quick. You can quickly integrate it twice. Do you agree? Integrate it twice and get the solution to this problem by imposing these boundary conditions. So, you know, you may ask me, why am I doing approximate solutions to a problem that's this easy? You will see why. Okay? You will see why. So we know that the approximate solution to the problem that I'm going to have here has to satisfy what? With a strong form Galerkin. Has to satisfy what? All the boundary conditions. All of them. Essential and natural. Okay? And so what I'm going to do, I'm going to consider an approximation that has this form. Okay? So I want you to start, if you're going to come up with your own approximation function, with your own fees, I'm showing you how to do that. I'm giving you the steps required so you yourself can come up with your own fees. Okay? To do that, you'll start with let's say I want a polynomial. So you start with this polynomial. And clearly, this is not a very good one. This does not does this satisfy any of the boundary conditions? If I put x equals 0, I get a sub 0. If I put x equals L, I get a sub 0 plus a1 plus a2. That's not a very good approximate solution, because the approximate solution in the strong form Galerkin has to satisfy all the boundary conditions, essential and natural. In this case, they're all essential. They're not, none of them are natural. So if I impose them, let's impose them. So at U0, what do I get? This go away, right? So then I get U sub 0 equals A naught. So I know that A naught must be 0. At least I know that for sure. At UL, I know that UL, the approximation function, has to be 0 because that's an essential boundary condition. We already stated that here. This side is fixed, right? For that reason, I'll put this in here. I already know that A sub 0 is 0, so I get A1 plus A2. Can you follow that? A1 plus A2. That's equal to 0. So I can write A2 or A1 in terms of each other. So I get A1 equals minus A2. And if I plug this back in here, knowing that A naught is 0, then I get this equation here on the left-hand side. And if I factor out A2, then I get this equation here. So this is the form. This is how the approximation function needs to look like for me to be successful using this method. So if I want to add another term, let's say I want to do a two-term approximation. I want to add another term here. Then what you will do is add the other term. In this case, I've done that. Add another term. And then when you add another term, you should check again that things do make sense. First of all, does it look complete? Well, yeah, I went from squared to cubed, from linear to square, so that looks complete. Does it still satisfy those essential boundary conditions? Let's make sure they satisfy them. Because I added another term, what if I made a mistake? So at x equals 0, do I get 0? Very well. If I put x equals 0, do I get 0? Yes, I do. So then this is a great approximation function. Is it sufficiently differentiable? Can I differentiate it? What was the order differentiation of my differential equation? Second order. Can I differentiate this twice, at least? Yes. So that's great. I have a great approximation function. And without going even further, I want to ask you a question. The exact solution, does it look like it has polynomials? The exact solution is a polynomial. I mean, if you integrate this, you can actually solve this, right? I can integrate this once, twice, and then impose these boundary conditions. You agree that the exact solution is probably a polynomial? Yeah? Well, so since the approximation function I'm selecting has polynomials, do you think I'm going to get the exact solution using this approximation technique? Yes. Actually, I'm going to get the exact solution. I'll show you that. We'll get the exact solution, which is kind of cool. So, but let's assume for a second I'm wrong. And then I plug in this approximation function into my differential equation. The question is, what do I get for that? Will it be equal to 0 when I substitute this there? If I substitute this approximation function into my differential equation, do I get that differential equation to be equal to 0? So if I substitute that here, will I get 0? No, because I have C1 and C2, right? It will not be equal to 0, right? So we'll call that error residual. And I'll make the residual, again, I'll take this differential equation, make it orthogonal to each of the basis functions. And the basis functions I have come up with is phi1 and phi2, right? We just discussed that. These are the basis functions. And I'll take this, multiply by that, integrate that very nicely, and then take the differential equation, the residual function, multiply by the basis function number 2, multiply that out, and then the first equation gives me something very nice. It gives me the first equation, the second equation. I can solve them. Okay? I can solve this equation. Now the question I have for you is, if I go back to my differential equation, what the exact solution only goes up to what order? Look at the exact solution. Integrate it twice in your head. What? Should be basically a second order polynomial, quadratic. But if you look here, my approximation function that I chose goes up to cubic. So I think I'm going to predict that this somehow is going to go to 0 because it needs to match the exact solution. So if we do that, you will see here I did get 0, that second term, and there's an error. Instead of A should be C. I'll change that. Can you take a note again? But I get A1, C1 to be PL squared over 2EA. That's awesome. In fact, when I go back and I plug it in, I get PL cubed over 2EA times that, and that's actually the exact solution. That's exactly what we will have gotten if we had. So in this case, the approximate solution does match the exact solution. And the reasons are is because we chose a polynomial, and the polynomial was the space. So if you notice here, we chose basis functions which belong to the space which contains the exact solution. So it's very abstract, but I want you to think about it. It's not that hard. If the space of functions, right, the space of functions that solves that partial differential equation or differential equation, if the space contains those functions, then if I selected those functions, then I should be able to get the exact solution, right? Because I'm selecting functions that make up my approximate solution. Okay? Is everybody clear on this? Sorry? Okay, so I have a space of functions, and I'm going to make it more simpler for you. I have e to the x, I have polynomials, I have trigonometric functions, I have hyperbolic functions. These are the space of functions I could have, right? If the exact solution to the problem has trigonometric functions in there, and I happen to select trigonometric functions from my basis functions, then I'm going to get the exact solution. It makes sense because I selected them from the space of functions that contains the exact solution. Yeah? Okay, so let's go to example 3. I'm not trying to bore you. These examples have different things. Okay? In this third example, which is in the book, my book, is a differential equation of second order, but what makes it different is that I have a boundary condition that's essential, that is non-zero. Okay, so I have a non-zero boundary condition. And then I also have a natural boundary condition because it's derivative of a primary field of interest, and this one is equal to 0. So this is what makes this problem a little bit different. But the process is the same. The process is the same. So I want you to know that the essential boundary condition, that this is not 0, is non-zero. And so somehow we have to account for that. And so let's start with considering an approximation of this form. So I will start with u tilde equals a naught plus a1x plus a2x squared. I'm going to impose this boundary condition. So when I plug in 0 here, I get a naught equals 1. Okay? So I got what a naught is. And then u prime 1 equals 0, so I'm going to impose that also. And I get a1 plus 2a2 equals 0. And then a1 becomes a function of minus 2a2. And I plug it in. And I get u tilde equals 1 minus 2a2x plus a2x squared. And you can see here, if I rearrange all these, I get 1 plus a2 x squared minus 2x. Okay? Now you quickly see something very interesting. You see this one here doesn't have a coefficient of a1 or nothing? Yeah? Everybody can observe that? I'll give you a couple of seconds to examine that. Right? So this one is alone. It's by itself. Okay? And so if we go back and remember when I defined this problem, I talked about w tilde equals something plus basis functions times unknown coefficients. Which is the one that's alone? That one. That's the only thing that's alone with no coefficients, right? So in the example I gave you right now, just right now, 1 belongs to this guy, the number 1, because it has no coefficients. But you can see that that 1 makes sense that goes with that, because the purpose of this guy is to satisfy the non-homogeneous form of the boundary conditions. And you can see that here. In this example, right? This phi sub 0 is 1 here, and you can see that by me setting this equal to 0, x equals 0, this is 0, and I'm left with 1. Can you see that that's the purpose of that? Is to make sure I satisfy this essential boundary condition. That's the purpose of it. And so now if I want to add another term, I can add another term. So that's my first term, my second term, so I make it cubed. And then I just made it minus 3x. But now that I add another term, I have to check. I have to check something. I have to check whether it's complete. I have to check whether it's sufficiently differentiable. I have to check that the basis functions I'm selecting, that they satisfy the homogeneous form of all the boundary conditions. They have to satisfy that. And we will check that now. Okay? And so, is it sufficiently differentiable? Can I take 3 times? Can I take derivatives over and over of this function twice at least? I can. Does it look complete? Yes, it does. So now I want to verify that this approximation function satisfies the essential and natural boundary conditions. And so if I plug it in 0 with the extra term that I added, it works out very nicely. I get 1. That was the boundary condition of the problem. And if I do u prime 1, I also get this equal to 0. So this approximate solution is a great one. It's a really good one to actually use. Now, I will tell you this. The exact solution of this problem is not a polynomial. It has exponential functions. So this is a true approximation of this problem. It's not going to give you the exact solution. And so now, again, I'll repeat the process, but it's basically, I take my partial differential equation, I form the residual function, and I make that orthogonal to each of the basis functions, phi1, phi2. Now, in all these examples, I've done 2 terms, right? But I could have done 3, 4, 5, 6 terms. I can do many, many terms. Okay, but I think I'll bore you if I do that many terms. Plus, it's more work for me, because then I have to solve them. Okay, so I'm not going to do that.
How come we didn't include the 1 for VX? Isn't that part of like the basis?
No, very good question. So your question is, to make sure for the video, is why phi sub 0 is not included in the set of basis functions. Let's assume I do that. I include phi sub 0, and I made it orthogonal to phi sub 0. How many equations will I have? 3. How many unknowns I have? 2. That's a problem. I have more equations than unknown. That's one issue. Second issue, the only purpose of that phi sub 0, the only purpose of this phi sub 0, its only purpose in life is not to be a basis function. Its only purpose in life is to satisfy non-homogeneous form of the boundary conditions. Because these guys will satisfy the homogeneous form of the boundary conditions. So you're left with this guy. That phi sub 0 has to take care of the rest. Has to make sure that anything that's non-zero in the boundary condition is taken care of there. Okay? Excellent. So if I go ahead and do these calculations, equation 1, equation 2, I get this set of equations, 2 equations to unknown. I can solve for C1. I can solve for C2. And if I plot the solution, that's the exact solution plotted with a strong form Galerkin. And you can see here that it's outstanding. And the exact solution is not a polynomial, by the way. It's an exponential. I believe it's an exponential. It's going to have e to the x, that kind of solution. So I don't know if this is exciting, but isn't this a different way of solving differential equations? Right? So now I want you to connect you with me a little bit now, a little bit better with finite elements. So if the solution to my partial differential equation for a solid mechanics problem that's highly complex has e to the x, has trigonometric functions as exact solution, that would be really tough to actually solve. I mean, if that was really a solution to these problems, it would be very tough to solve these equations for a very complex domain for which the solution has trigonometric functions e to the x. If I can barely solve a partial differential equation in 1D, then this methodology I'm teaching you right now works because I can use this for any differential equation. And my approximation function that I'll be using moving forward, I want to use polynomials. That's to my advantage. Polynomials are easy to use, and you can represent behaviors in a very clean way. For example, if I want to represent a constant temperature solution, I can do that. If I want to represent a linear temperature variation over a structure, I can do that. If I want to represent a gradient, maybe not as good, but if I combine linear behavior with constant plus quadratic, maybe I can get closer. And so the goal is really to come up with a systematic approach of solving these equations. And I think I'm getting you there little by little. Any questions so far? We have plenty of time today, so if you have any questions, feel free to ask me. I can repeat any of these examples. But I'll go to example 4 then, if there's no further questions. Example 4 is a little bit more complicated, but it's not that different. And you need to have a very, very focused mind right now, because there'll be a lot of math here. But there's 2 differential equations here shown, and there's 2 unknowns here, 2 primary variables of interest. One is M, and one is W. So in this case, in fact, if you were to determine how many boundary conditions you will have 3 at x equals 0, and then 3 of them at x equals L. So this is a little bit more complicated problem, but it's a problem that can come up. You can have a set of differential equations, not just one. You can have multiple of them, okay? And then you have to approximate a solution to that problem, okay? And situations like these require a little bit more thought. And what we're going to do is that this term from Galerkin, so the approximation function has to still satisfy all the boundary conditions, all of them, essential and natural, at x equals 0 and x equals L. So that doesn't change. And but we're going to follow the same process as before. And the process is we're going to form a weighted residual. We're going to follow the same process. But here, what I'm going to do different is I'm going to multiply this first equation by a weight function plus the second equation by another weight function. That's the way I'm going to approach the problem. And so if I were to do it, this is the way it looks. Can you see that I have a single integral over the domain? It's a single integral 0 to L over the whole domain, okay? And that is a single equation. How many equations you see here? One equation. And that here, what I want to point out is that this is actually equivalent to the fundamental lemma of calculus variation. If I were to use the fundamental lemma of calculus variations, I will end up with the 2 governing equations. Why is that? So what fundamental lemma of calculus variation says is that for any admissible arbitrary functions I select here, that if this multiplication plus this multiplication equals 0, that if for any variations of this, that the what's inside the integral is equal to 0. In this case, those represent the governing equations of the problem. Okay, I just made it slightly more complex by adding another term, but it's nothing to be concerned about because the process is the same. I want to level you with me a little bit, and I want to ask you, what are the unknowns of this problem? What are we trying to solve for? Just to remind everybody what we're trying to do here. Sorry? Yeah, we're trying to find a solution to M and W. And there's 2 differential equations here, okay? And so what we've done is taken the first differential equation, multiplied by V1x, taken the second differential equation, multiplied by a weight function V2x. And now what I need to do is to substitute an approximate solution on M, an approximate solution on W, and then make the error, this error, orthogonal to the set of basis functions, and make this error orthogonal to the set of basis functions in a single equation. To accomplish that, I need to do something. I need to first come up with approximation functions. And sorry, I cannot do an example on this with numbers because it will be very time consuming for 2 equations, and then substituting the approximate solutions to each of them will take a significant amount of time. So instead, I beg you to really work it out at home. Just take two terms here and then 2 terms here, and kind of see if it works out. Okay, and please wake up if you're falling asleep. Okay, let's pay attention. So what I'm going to do, I'm going to find an approximate solution to m tilde x, and that's going to be just like before, but this one is going to have n terms, so n unknowns for d. Okay. And I'll have an approximate solution for W tilde. This, I'm going to have m terms. Do you agree with me that I can have different number of unknowns for this approximation to that one? If I have 2 terms there, I can have 3 terms there. I can have them different. Okay? And so I'm going to put this in matrix form just like before. So what is the size, the dimensions of this vector here? N by 1. N by 1. Your answer is n by 1. That's incorrect. It's 1 by n. And it's here. It's shown here. 1 by n. Okay? What is the size of this D? N rows by 1. Okay? So that 1 by n times n by 1 gives me 1 by 1. I get a scalar quantity. Okay? So that's scalar quantity, I'm sorry. And then I repeat that here. Okay? I repeat that here. And this is approximation. So what are the unknowns now? What are the unknowns now? Because these P's I'm going to select. This C I'm going to select. So what is the unknown of the problem now? I reduce the problem to unknowns of what? C's and D's. So now I have to find just the C's and D's. Now how many unknown coefficients I have on M? Sorry? N. How many unknown coefficients you see for W? M. So how many unknowns you expect then, total? N plus M. So how many equations you expect at the end of the day? N plus M. So you want to keep track of this. I don't want you to be just doing stuff and not understanding what you're doing. You need to really pay attention to the size of the matrices and things like that. Okay? And so, but there's a problem here, and it's actually quite interesting. So I have now basis functions here, and the question is how do I pair them up? Because I have 2 weight functions here, right? So we need to pay attention to that. And to do that, the idea is that you'll write your differential equations, and then you look at the dominant term. The dominant term is the one with the highest derivative. So the first equation, the highest derivative, is given by these 4 primes. So that's driven by what variable? M. For the second differential equation, what is the highest derivative? W has it. So what I need to do is pair the correct approximation function with the correct differential equation. So here I can see quickly that since M is a dominant term, that these are the basis functions I want to use to multiply with that differential equation. And then for the second differential equation, since W is the dominant term, I want to use phi as a set of basis functions which I'll make orthogonal to the error in the second equation. Is that clear or is it unclear? Remember, before we were taking the error and making it orthogonal to basis functions, right? But now I have 2 sets of basis functions because I have 2 approximation functions, here and here, right? So what I'm trying to do here is trying to pair them correctly so that I can construct the weighted residual correctly. And so if I were to plug in the solution for M and for W, the approximate solution, this is what I get. Okay, so I just substituted that here, and I made it orthogonal to C for the first one, and the second equation I made it orthogonal to phi, which is correct. I paired them correctly, and now I have a system of equations, actually. See if you agree with me. Do I have a system of equations? Do I have more than one equation here? It's a mind bender, I know, because even I was going through this myself, and I was trying to think through it. So pay attention to what I'm doing. So C as an example, is what is the dimensions of C, matrix form? 1 by n. So phi transpose is what? N by 1. Okay? So here what I have, in fact, if you were to check this out, you have n plus m equations here, believe it or not. You have n plus m equations. It's not clear to you yet, but I think I'll make it clear in a few minutes. So all I have to do is follow the process. The process is I took the first equation, I substituted the approximation function in there, I substituted this approximation function in there, in both of them. I took the residual, isn't this the residual error for the first equation? I made it orthogonal to the space of basis function, which corresponds to the highest derivative, which is m. So that's why I said it's C and not phi. And then I continue to add the weighted residual. So I have the second equation, which has the residual error, and I made it orthogonal to the set of basis function given by w, which corresponds to the highest derivative in the second equation. And I'll multiply everything out. Let me multiply everything out and see what happens. So let's multiply everything out. And if I multiply everything nicely, and I put it in matrix notation, okay, I'm going to spend a couple of minutes, and I'll be quiet. I'll try. I'm not very good at it. I want you to multiply this times that, and tell me whether you get what you see in the top. Okay, and some of these terms are missing because they're in the right-hand side. But just do an example in your head. A couple of minutes right now. Okay, let's do a couple of examples. You can see it works out. So this term, C transpose times this C fourth prime D, that's basically this term here. This one here multiplied by D, that gives me that term. And then this multiplied by that term is basically B, so phi, C transpose times B times phi double prime. You can see that there. Okay. These are the basis functions. Okay, you know them. You know these basis functions. So you can perform these integrals fairly quickly. And then the second equation actually shows up in the second row, and you can see here C phi transpose times C double prime. So that's, is this an error of my part? I think I have an error. That's great. How do I fix this error? How should I fix it? This should be D. This should be D. So phi transpose times D times C double prime, that's that one. So I'll fix that. That's D. This should have been C. So phi transpose times C, phi fourth prime. Can you take a note so I can fix this? Okay. And then I'll post the notes so they're correct. And you can see that if I multiply this, I do get a lot of the terms. Can you see that happening? If I multiply this out, I get a lot of the terms, the remaining of the terms, actually. So what are the unknowns here? D and C. What is the size of D? So you may not remember, and I actually don't remember myself, so I'll look it up. So D, I have D n unknowns. For C, I have m unknowns. So then D, the size of D is what? N rows by one column. C has m rows times one column. So then this row, this column has how many rows? N plus m. Very nice. It works out. Let's look at the size of this matrix right here. This matrix alone. Let's think about it. C, I believe this was the one that goes with n. Sorry, the m. Let's see. C goes with n, so I must have, we talked about 1 times n row columns. So let's see. So this one is how many I have there then? N times 1. C is 1 by n. So how big is this? N by n. Okay. Let's look at this here. If this is n by n, and then we'll look at this here. Phi had m. It was 1 by m, but the transpose is m by 1. This is 1 by m. So what's the size there? M by m. So at least we know the diagonals have n terms, and the diagonals here have m terms. So the size of this matrix is n by m, n plus m. And then you can check the other ones. The other ones will be a combination. You can check it. And so then I have n plus m equations, n plus m unknowns. You can invert. You can solve this very quickly. Integrate this, invert it, and then solve for the d's and c's. Okay? This example, you can do it by hand. I recommend that if you go home, just make n equals 1 as an example, and then make m equals 2. Just don't do something very long. And then work it out by hand, and you will see this is going to work out. It's very important for us to learn how to put it from this format to this format, because that's the point of finite elements, is to be able to formulate the problem in a way that you can systematically solve a differential equation. Okay? And you want to put every problem in the same format if you can. Okay? I recognize this is not a very easy subject, but I also know from my own experience that it's through practice that you'll become better. So while I won't give you homework due next Thursday on this. I decided not to. So the only homework problem you have for next Thursday is the trust problem. I do want to make sure everybody here understands that these 5 examples I've given you today should be example problems you work out by hand in the next week. At the very minimum. I'm not giving you a homework on this next Thursday, but at very minimum, I do think you guys need to work it out by hand yourselves. And I do understand that there's some typos, and I'll correct those. And for those listening in the video, I'll upload the corrected charts, and hopefully through the sound system you've acknowledged that there's some typos here. But they're not major, and you should be able to do fine. So that's example 4. And now I'll move to example 5. So each of these examples are different, but they encompass almost everything you should be able to see in this class. So let's look at example 5. Example 5 is a 2D domain. Everything I was doing was 1D. I'll do a 2D domain. In a 2D domain, this actually is a very standard problem in structural mechanics. This problem is a Laplacian. It can be solved for a membrane, a 2D membrane, like a carpet hanging. It could solve a torsional problem. It can solve a potential flow problem. It can solve even a heat transfer problem when conductivity equals 1, as an example. It can solve the moisture or diffusion problem, and so forth. So you can solve a lot of problems with this. So it's worth discussing. So in this 2-dimensional problem, what is the primary field of interest? Only 2 people know the answer? U. We're solving for U. We're not solving for X or Y. X and Y is the coordinate, is the domain of the problem. In this particular example, I'm making a domain to go from -a to a in X, and minus a to a in y. So it's a square domain, very simple. And we're going to specify an essential boundary condition that this quantity be 0 at all the edges of this square. Okay? And then I'm going to use a strong from Galerkin. The exact solution is this one. So in the center of that square, the solution is that. I also have an error here, because not u at 0 is 0. It's u at every single edge is 0. Okay? So the edges are at x equals minus a, at x equals a, y equals a, and y equals minus a. So those are the edges. That's where we're saying is 0. The center is free to be whatever it needs to be. Okay? So we'll fix that as well. All right, any questions on the problem statement? Okay. Fortunately for you, since it's a 2D problem and it's very complicated, I'll give you the approximation function. I'll be nice. I'll give it to you. The approximation function for one term just looks like that. But what I'll ask you to do is to check whether it does satisfy the boundary conditions. And you can do that. If I substitute x equals a, do you agree you get 0 at one edge? If you put x equals minus a, do you get 0 at the other edge? Very good. Y equals b, do I get 0? Yes. Because, oh, another error. This should be b. I'm so sorry. I typically will teach this by hand, but PowerPoint, just creating slides can cause errors. So this should have been b. I'm sorry. This is correct. This is correct. It's a square. It's not a times b, right? It's a square a by a. So it does work out. Y equals minus a, 0. Y equals a, 0. So all the edges, u is 0. That's very good. Satisfies the essential boundary conditions and natural boundary conditions. In this case, there's no natural boundary conditions. All the boundary conditions are essential. If I were to go to a two-term approximation, I'll add another term in this manner. And if you notice here, I have these terms repeated. These terms are there to ensure that essential boundary conditions are satisfied in the second FEA. Okay? So let's run through how we will do this. One-term approximation, it's very simple. You take this residual, you form that residual, you plug it in here, okay, and that's what I've done in the bottom. You take this approximation function, substitute it here, okay, and I'll make that orthogonal to P1. So that's what I've done there. And my students from 261A have done this, a homework problem actually. And so they went through that pain. You're not going through that pain. You will go through a different pain later, through a different problem, right? And I use these examples so those that took 261A cannot repeat that in their homework. So they have to do a different one, okay? You get the solution. You actually solve. You can solve for C1. And when you solve for C1, you get, at the center, you get 0.3125, which is actually only 6% off from the exact solution. Just one term gave me 6% off. That's pretty impressive. Then I will do two terms approximation. Two terms approximation. Substitute that approximate solution in here. So I form the residual function. I make that orthogonal to each of my basis functions. So my first one is P1. My second one is P2. And I'll make a orthogonal to Phi1 and then Phi2. And I have two coefficients, C1 and C2. Solve for C1 and C2. And I get 0.2922, which is about 0.5% from the exact solution. It got even better. And adding a third time, I don't think it's worth it. It's going to be like 0% off, okay? If you want to learn how to do it in Mathematica really quickly, very quick, I actually did it in 2 steps. This is Mathematica. I defined what Phi1 was. I defined what Phi2 was. Then I make the approximate solution for one term is C1 times Phi1. So for one term is that. For two terms, you will have C1 times this one plus C2 times Phi2. So I have 2 of them I'm trying out. And I'll create the residual. So I'll do the residual. And you can see here how I did it. I'm not going to go through them. But just with a simple very simple functions, I was able to get the value for C1 for one term approximation, and then for two term approximation, I get C1 and C2 with very little effort. Okay, so I'll let you look at that at home because I don't know if you use Mathematica, but if you use it, then you can borrow this for your homework. Okay, but you can also do the same thing in MATLAB and so forth. Okay, so very, very good. We, for the first time, have What is the question?
Okay, so you said earlier that when the okay, all examples you went over, you assume that the basis functions are the same that the weight function.
Yeah.
What are the consequences if we don't follow that rule?
So if the question on the audience is if I don't select the weight function to be equal to the basis function, and I want to answer this in two parts. The first part is there is a way to do that. You can use functions that are not the same as the basis functions. And that method is called Petrov-Galerkin method. And it's discussed in my book more with examples. Okay. There's also another method called collocated method. We'll also select functions that are not the same as the basis functions. So you can do that. But for finite elements, it suffices to just focus on using the weight function to be equal to the basis function. The second part of that question is consequences. Are there any consequences for using other functions that may not be the basis functions? One consequence is that you may have more difficulty converging to a solution. That's one potential issue. But as you can see in my book on Petrov-Galerkin method, it usually does work out and can be successful as well. Okay. So with that said, I did not finish, so I do have one more slide. And that slide is that strong form Galerkin, while it is amazing, as you saw, because I don't know if you noticed here, did you have to do anything? You know, I don't know if you remember when you took differential equations and partial differential equations, you had to do, there's special solutions for each class of differential equations and partial differential equations, right? So if I were to solve a partial differential equation for a very complicated problem, I cannot sit down and start creating the specialized solutions, right? But what I taught you here is a way of systematically cranking, you know, step A, B, C, D, E. You follow the steps, and it's the same step for every single one of these differential equations. And if you follow these steps, you get the unknown coefficients. And not only that, we took a differential equation or partial differential equation, and in the end, we got what? A system of what? Algebraic linear equations. They could be nonlinear, but the examples I gave are linear. So we're getting there little by little. But what I want to point out is that this strong form Galerkin has some difficulties. Because the approximate solution I have to select, okay, if I had a fourth order differential equation, I had to select approximate solution up to at least fourth order. So that's kind of a challenge. But not only that, the biggest challenge is actually you have to satisfy the essential and natural boundary conditions. You have to satisfy all the boundary conditions. Now let's take an example, a problem here. Let's take a problem here. Let's take a problem of an aircraft with a load applied at the wingtip. Maybe somebody dropped something, want to simulate the impact damage of that wing deforming. By the way, the number one problem that occurs in industry, somebody dropping a tool. And then the second problem is somebody asking you, Vinay, do you think this structure is okay? That's my typical day, okay? Christian, I think you're laughing because I think you work in the industry, so you probably agree with me.
CSAI?
Yes. You probably work in aircraft. Okay? So people will drop tools in a composite, and you have to figure out whether the composite is okay or not. So that's a typical analysis I will do, okay? There's a reason why we're doing some research with you on impact damage, right? Was because that's a #1 problem in industry. But just imagine you have to come up with approximation functions that have to satisfy a loading condition. It's very tough. But what I can do is to come up with approximation functions that satisfy essential boundary conditions. For example, like a cantilever beam. Or I can satisfy the wing fixed at the very root. Those are boundary conditions I can actually impose in my approximate solution. But imposing boundary conditions and making sure my approximation function is exact to the load I'm applying, and at the same time satisfy deflection boundary conditions is very tough. And not only that, my approximate solution also has to be sufficiently differentiable. In this case, if it's a beam, a fourth order differentiable. In finite elements, I want to have a way of approximating solution maybe with linear polynomials, or maybe quadratic polynomials. Linear polynomials are mostly used, but also quadratic. So I don't want to have an order differentiation that's too much, and also I don't want to have to satisfy all these boundary conditions exactly. Okay, and so for that reason, there's some challenges, and we won't be using strong form Galerkin to develop finite elements, but we'll use strong form Galerkin as a basis to develop the next theory or approximation method, which is called weak form Galerkin. And then that will be the basis of finite elements. That will be what we'll build upon. Okay. So with that said, is there any questions on anything I said? Can you see the challenges with me, or you want me to revisit some of these challenges with you now? As an example, just to give you one more example, since we have 16 more minutes, but I won't take all those 16 minutes. If I have this part, I have this beam on the transverse loading, and now I have, say, a moment that I want to apply. With strong form Galerkin, not only I have to satisfy these essential boundary conditions, I have to also come up with an approximate solution that satisfies that moment loading applied. So I've made it's more challenging. You can do it. It's very doable, but it's not ideal for finite elements. Okay. So with that said, you have a good weekend, and I'll stay here